Okay, so let us continue. Last time we proved that if the radical of an ideal is a maximal ideal, then I is primary. So, last time we saw an example where radical is prime does not really imply that the ideal is primary, but if the radical is primary, radical is maximal, then the ideal is primary. And one more thing that one can say is that I is primary need not necessarily imply that I is a power of a prime ideal. Straightforward example is I is, I think we looked at, did we look at this example in kxy, k a field and polynomial ring kxy. This is a primary ideal, but this is not power of any prime ideal. There is only one prime ideal containing I, right? What is that prime ideal containing I? The maximal ideal generated by xy, right? That is the only prime ideal containing, or in other words, radical of I is m. We are in this situation, radical of I is m, but m is not equal to I, m square is contained in I. What would be m square? This is x square xy y square. M is so take m to be xy, then m square is this. So, m square is contained here and I is contained in m. So, m square strictly contained in I, strictly contained in m, and m is the only prime ideal containing I. So, I is not equal to p power n for any prime ideal. Yeah? Yeah, this is properly contained in, because y is not here, right? xy is here because y is there in I. So, xy is there, right. So, this is contained here, but this is strict containment, this is also strict containment. So, I cannot be equal to any prime ideal, I mean power of prime ideal. Okay, now, so what we were looking at is kind of a generalization of the prime decomposition of integers into the case of ideals in prime Noetherian ring. So, first let us observe something. Suppose if q1 and q2 are p primary, okay, can we say, what can you say about q1 intersection q2? First of all, let us look at the radical of q1 intersection q2. What is radical of q1 intersection q2? Properties of, by properties of radical, this is equal to radical of q1 intersection radical of q2, but both of them are p primary. So therefore it will be, this will be p, this will be p. So this implies that this is equal to p, sorry, okay. But that does not mean that the intersection is primary, right. So let's say, let's see if we can prove that it is primary or not. I mean, let's check, let's verify whether and x is not in q1 intersection q2. We want to see if some power of y belongs to the intersection, okay. Now x is not here implies x is not in either q1 or q2, right. So suppose x is not in q1, x is not in the intersection means that x is not in one of them. So suppose x is not in q1. Now xy is in q1, x is not in q1 and q1 is p primary, and so there exists n in n such that y power n belongs to q1. But what we want is some power of y in q1 intersection q2. How do you get it? Y power n belongs to q1. What does that mean? Y belongs to radical of q1, which is p. But now you can, y belongs to p and p is also radical of q2, right. It is also radical of q2. That means some power of y belongs to q2. So if you take maximum of m and n, that will be in q1 intersection q2. So that implies q1 intersection q2 is p primary. So if I take two primary ideals and intersect them, we get a p prime. I mean, again, if I take two p primary ideals and intersect them, we still get a p primary ideal. Now, which are the ideals that can be written in the form of intersection? Such ideals are called reducible ideals or decomposable ideals, okay. So an ideal I is a proper ideal is said to be reducible if I is equal to I1 intersection I2 for some proper ideals I1 properly containing I and I2 properly containing I. That means it is the intersection of two bigger ideals, but bigger proper ideals. For example, in Z, if you take 6Z, can you write 6Z as 2Z intersection 3Z? this is proper, I mean this is 6z is a reducible ideal. What about 4z? Right. So, if I have, see in Z this is easy to see. What is this intersection? LCM of, yeah, plus is GCD of M and N, intersection is LCM of M and N. So, LCM of M and N is 4, implies either M has to be 4 or N has to be 4. Right. So, therefore, this is not reducible. Such ideals are called irreducible ideals. So, an ideal which is not reducible is called an irreducible ideal. So, if the ideal is irreducible, if I is equal to I1 intersection I2, then either I1 is equal to I2 or I1 is I mean I is equal to I2 or I is equal to I1. That is, I is irreducible if for some proper ideals I1 comma I2, I is equal to I1 intersection I2 implies I is equal to I1 or I is equal to I2. So, 4Z is an irreducible ideal in Z. Can you generalize this? What are the irreducible ideals of Z? Yeah? P power n
containing any number p, like p to the power n where n is not equal to 1.
How about P, I mean P itself, Pz is this? This is irreducible, right, because this is maximal, right.
So, where n is not equal to 1.
So, if P power n Z, if n is equal to 1, even then it is prime, I mean it is irreducible, right.
If a number can contain at least a product of two different primes,
then it is
reducible.
reducible. Or in other words, what are the irreducible ideals of, see if I can write P1 power alpha 1, P2 power alpha 2, if there exists something like this, then you can, and whatever, you know, whatever k, this is k where k does not have P1 and P2 factors, then you can always write this as P1 power alpha. So, this Z I can write it as P1 power alpha 1 Z intersection with P2 power alpha 2 k, yeah, Z, right. I can always, so if there are two distinct primes in the prime factorization of that integer, that ideal will be, the ideal generated by that integer will be a reducible ideal, or in other words, an irreducible ideal is in Z is of the form P power alpha for some prime P and for some positive integer alpha, right. So, if nz is irreducible, then n is equal to p power alpha for some prime p and alpha in N. So, does that suggest something? These are irreducible implies primary. These are all the primary ideals of Z, right. So, let us see, let us start with a irreducible ideal. Let I be an irreducible ideal. Okay. Let's look at. So the question is, see, in this case, in the case of Z, the irreducible ideals are all same as primary ideals, right. But Z is a PID. It's much stronger than being Noetherian ring. So a priori there is no reason that to believe that in Noetherian rings irreducibility will imply primality or not, primary property or not. But still, let us see what happens. Okay. So let's start with x y b in I. Okay. I want to see if whether I is primary or not. One way to do this slightly easier to handle the situation is, so we are looking at I ideal in A. I is irreducible if and only if, okay, so for 0 is irreducible in A mod I, right. If I is reducible, then I can be written as I1 intersection I2, where I1 and I2 are proper ideals properly containing I. So I can take their images into A mod I and write 0 bar as their I1 bar intersection I2 bar. Similarly the converse. So therefore 0 being irreducible or reducible in A mod I is equivalent to saying that I is being reducible or irreducible in A.
So it may be possible that I1 bar intersection I2 bar is strictly contained in I.
So that's what we are saying. If I is equal to I1 intersection I2, that would imply that you take the same equation to the I bar is I1 intersection I2 bar.
We are taking I contained in I1.
Yeah. I is reducible implies there exists ideals I1 and I2 containing I, properly containing I, and proper ideals such that I is equal to this one. Now look at this equation modulo I, look at this in A mod I. In A mod I, this is I bar is 0 bar, 0 bar will be written as I1 bar intersection I2 bar. That means 0 bar, 0 is reducible in A mod I. Conversely, if 0 is reducible in A mod I, that means I can find two ideals I1 bar and I2 bar such that 0 bar is equal to I1 bar intersection I2 bar, proper ideals properly containing 0 bar. But then any ideal of A mod I is of the form some J mod I, where J is an ideal containing I. So therefore just pick those inverse images of I1 bar and I2 bar, bring it back to A, you get I is equal to this one. So therefore being reducible or irreducible, 0 being reducible or irreducible in A mod I is equivalent to the ideal I being reducible or correspondingly irreducible in the ring A. So therefore we can, instead of this, we will assume that our ideal I is 0. In A. Okay. We want to check whether it is primary in A. So, let x y be equal to 0 and x is non-zero. We want to check whether y power n is 0 for some n. Okay.
It should be A mod I.
No, we are, so that is what I am saying. If we can look at, certainly we can look at A mod I instead and then bring it back to I. Instead we just assume that I is 0, because once we prove this, the other one can be deduced from here. You start with some irreducible ideal, go modulo that and then use this result. Okay. So, suppose x y is 0 and x is non-zero. Now, you have a nice increasing chain of ideals sorry, annihilator of y. See, our aim is to prove that y power n is 0. Okay. We have a chain of ideals. Once you see an ascending chain, what comes to your mind? Whether it terminates or not. So, to make sure it, suppose it terminates, that is the condition on A. If A is Noetherian, then this will terminate. So, suppose A is Noetherian. Then there exists n such that annihilator of y power n is equal to annihilator of y power n plus I for all I bigger than or equal to 1, right. The sequence terminates implies it is after a finite stage everything is equal. I want to say that y power n is 0. Suppose y power n is non-zero. Okay. Now we know that x y power n is 0, because x y itself is 0. Okay. Yeah. So, see, we have said that 0 is an irreducible ideal, that is our hypothesis. We have not used this fact at all. Okay. Now, y power n is non-zero. Suppose we can get a contradiction, that should be on this hypothesis, because this is the something that we have not used yet. So, one way to see is check is whether 0 can be written as intersection of proper ideals. What we know is that x y is 0, okay, but this ideal generated by x and y, this need not necessarily be 0, because the product x y is contained here, but that need not be this, right. For example, in the case of z, intersection is intersection of m and n is LCM of m, it is not the product of this generated by, need not necessarily be generated by the product. So, we can't expect this. How about y power n? Suppose I have A belongs to x intersection y power n. What does that mean? I have Ax is in the ideal generated by an element, you start with some element B in the intersection, B is in the ideal x. So, therefore, B is of the form Ax, but that is there in y power n. So, I can write this implies that Ax is equal to Ry power n for some n. Now multiply by y on both sides. What do you get? R Axy is 0 because xy is 0. That will imply that Axy equal to 0 equal to Ry power n plus 1, and that would imply that R belongs to annihilator of y power n plus 1, but annihilator of y power n plus 1 is same as annihilator of y power n, and that implies Ry power n is 0, or in other words Ax is 0, or in other words sorry I wrote B. B is equal to Ry power n, that is 0. That means this intersection is 0. This implies B equal to Ry power n, which is equal to x equal to 0. This implies x intersection y power n plus 1, this is 0. So this is 0. Not only that, both of them are non-zero. So this, if y power n is non-zero, this contradicts the assumption that the hypothesis that 0 is irreducible. So the contradiction implies that some of our assumptions are wrong. So the only assumption that we have made is y power n is non-zero. So this implies that y power n is 0, and that implies that 0 is primary. So if we include this in our hypothesis that our ring is Noetherian, then what we have proved is every irreducible ideal is primary. So ideal in a, so let is this clear? Every in a Noetherian ring, every irreducible ideal is primary. So now what we know is that suppose you start with a reducible ideal, okay, which means you can write it as intersection of I1 and I2, some proper ideals contained in properly contained in A and properly containing I. Now look at I1 and I2. Suppose I1 is irreducible and I2 is irreducible, we are through. I mean the decomposition stops there, you can't do further. Suppose I1 is reducible, we can further decompose. Suppose I2 is reducible, you can further decompose. How far you can go? I mean, can this process continue infinite times? The question is whether given any ideal in a Noetherian ring, can we express it as intersection of finitely many irreducible ideals? What is now we are no more in Z, we are in, okay, in Z one can easily write down, right, it's suppose your prime factorization is p1 power alpha 1 up to p k power alpha k, then the prime factorization is, sorry, the primary decomposition is precisely p1 power alpha 1 Z intersection So, the question here is whether we can, given an ideal in a Noetherian ring, can we express it as intersection of finitely many irreducible ideals. Suppose, so let's say suppose we cannot do that, okay, that means there exists some, yeah. So, what is that? So, suppose so let's write like this, let I be equal to I1 intersection I2. So, the claim is, what is the claim? Every ideal in a Noetherian ring is an intersection of finitely many irreducible ideals. So, suppose not, what happens? So, I mean, how do you write down a proof in the sense that, I mean, suppose this is not true, that means there exists an ideal with an infinite intersection. Okay, so let us write, suppose I is equal to I n n in n, let us say, let us assume it is countable infinite. Then what is the your J1 is I, then contained in, so take J I to be intersection J from I to infinity, yeah, J2. So, how do you say that this is yeah?
Can we argue like that if all INs are irreducible, then we are done?
No, here we have infinitely many. So, here why is this properly contained in? J2 is properly contained in, yeah, we can assume that. So, this is we have to assume that if I mean I is of this form with such that Ij does not contain intersection of the rest, because if Ij contains the intersection of the rest, then you can remove Ij, okay. And keep doing this, so let I be equal to intersection I n n in n with Ij not containing intersection of I n not equal to I, okay. Let J k equal to intersection n from k to infinity I n, then J1 is properly contained in J2, properly contained is an infinite chain in A, okay. So, that is a contradiction to the contradicts the assumption that A is Noetherian. Okay. So, that says that every ideal in a Noetherian ring is intersection of finitely many irreducible ideals, but in Noetherian ring we have proved that every irreducible ideal is primary. So, in a Noetherian ring every ideal has a primary decomposition. The primary decomposition is precisely what we said.
Sir, what is the use of that second assumption?
This assumption. See, if ij contains this intersection, the rest of them, then ij, I mean if I have some ideal I is contained in j, then I intersection j is same as j, sorry I, right. So, here the role of j is not there, j need not be there at all. Okay. So, in this case when you say that there exists a prime ideal which cannot be written as intersection of finitely many irreducible ideals, that is what we are claiming. Okay. Or in other words, there exists an ideal with such an infinite intersection, does not have a finite intersection of irreducible ideals, and from here for convenience we don't want redundant ideals there, I mean which containing the rest. Then say for example if I1 contains the intersection of the rest of them, then I1 is not there, I mean it is not needed in the intersection at all. So, we just throw away, I mean just for the sake of argument, to make it simpler, we can assume that, and we will, I mean see whatever the remaining, when we throw out, the remaining cannot be finite, because our assumption is that I is an ideal which does not have a finite primary decomposition. So, this has certainly an infinite, not only that it has finite, does not have finite decomposition, any primary decomposition has to be infinite.
So that means in the second assumption that should be n not equal to j.
So, this is n not equal, oh sorry not I, this is j, yeah. So, this condition will ensure that there are no redundant ideals. Not only that, this condition will say that at each step we have a proper containment. Okay. Let us look at some examples of primary decompositions. What is the primary decomposition of x square y? X square xy, sorry, x square y is a primary ideal itself. So, x square xy, this, so for the case of monomial, I mean it's finding primary decomposition is not always a trivial task, but in the case of monomial ideals it is very easy. Let me write down one exercise. Suppose I is a monomial ideal. What is meant by a monomial ideal? In polynomial ring K x1 up to xn, some polynomial ring. Monomial ideal is ideal generated by monomials, polynomials with only one constant. Polynomial is as many terms, yeah. So, polynomial is sum of monomials. So, suppose I is a monomial ideal in k x1 up to xn. Let AB be a monomial generator of I such that GCD of A comma B is 1, they are co-prime, no common factor. Okay. Then so write or set j I equal to I1 plus AB. So, AB is a generator. So, I can write it as, say for example, this one I can write it as ideal generated by x square plus xy, ideal generated by xy. Then I is equal to I1 plus A intersection I1 plus B. This is leave it to you as an exercise. Do you understand the assertion? I take out, so I will give you, I will take a look at an example. Let us do this example itself. I equal to x square comma xy. So here our I1 is the ideal generated by x square, A is x and B is y. So this is equal to x square comma x intersection x square comma y. But what is this? This is x. So this is x intersection x square comma y. Okay. So this is, now this is primary, this is primary. Okay. Let us look at another example. I equal to xy comma xz in kxyz. So apply the previous result recursively. What do you get? This one, this result. What you get is, this is equal to, sorry, xy comma x intersection xy comma z. But now this is same as
X comma x intersection means x intersection y x.
no xy. See this ideal. What is this ideal?
X intersection xy.
Huh?
It can be written
Can you see what this ideal is?
x intersection xy.
Ideal generated by x itself, because xy is there in the ideal generated by x. The second generator, so it is like looking at the ideal generated by 2 and 4 in Z. 4 is contained in the ideal generated by 2. So therefore this is ideal generated by x itself. But the second one, this is, this we can again use the previous result, z comma x intersection with z comma y, right. This one I can think of, see, z as I1 here and this as AB, right. So z comma x intersected with z comma y. So what we have here is now x intersection x comma z intersection y comma z. But now do you see some redundant ideals there? What is this intersection? X only, right. So this intersection we do not need this one, this is redundant, we can just remove this. This is equal to x intersection yz. Of course, you know, if you look this little carefully, you can write down that one very easily. Yeah. Yeah. X square xy xz z square in kxyz. So we can take one of these as AB and the rest of them I1. So this is equal to x square xz z square x intersected with x square xz z square y. Okay. Now what is this ideal? These both are contained in the ideal generated by x. So these two elements are not required at all in the generating set of I. So this is equal to x comma z square intersection. Now we have to split this again.
Sir, how much z is containing this?
not Z, xz,
XZ in
because there is a generator x. So if
Z is
yeah, now x square y z square, now we split this x intersection x square y z square and z, x z square, and what is this ideal? This will be x y z square, and this ideal would be yeah x square y z. Okay. So, using this property one can decompose monomial ideals very easily. I will stop with one example to show you that sorry, or we can further reduce it. Oh, this is contained. Oh, this is redundant. This is redundant. So this is x comma z square intersection x square y z. Yeah. See the decomposition need not necessarily be unique. For example, the one that we started with x square comma x y. Okay. Yes.
in the last one, how will we generate Y?
There is no y.
No, from the second last step you came to the last.
This is x. We just removed these two.
No, in the second last step.
This one.
Yes, sir.
No. See, this ideal is this ideal contains this one. I is contained in J, therefore I intersection J is I itself. So therefore this is not required in the intersection. That is a redundant component. Whether it is there or not, it is not going to make any difference. Okay. So see, look at this ideal. This one we looked at this primary decomposition x intersection x square comma y, right. One can also write this as x intersection x square comma xy comma y square. This is also equal to this intersection. In fact, this is equal to y power n for any n bigger than or equal to 1, any n in n or n bigger than or equal to 1. So this says that primary decomposition is not unique. Okay. So what is meant by not unique, or what, so what kind of uniqueness can we expect in primary decomposition? Yeah, the decomposition, see in the primary decomposition in Z, what we have is, or even in a normal UFD, what we have is some associates. So, or in other words, the primary components are unique in some sense. Whether we have something similar like that in this case of Noetherian rings, we will see that later.